very warm welcome to all my brilliant WAEC, NECO and JAMB candidates. Listen, have you ever wondered what gives compounds those beautiful colors, like the bright blue in copper sulfate? Or what makes huge industrial processes, like making fertilizer, even possible? Well, the answer lies in a special group of elements we're tackling today, transition metals. Seriously, mastering this topic is going to fetch you some guaranteed marks in your exams, so let's dive right in. Okay, focus up now. As you can see, our topic today is transition metals and their compounds. Now, this isn't just another chapter to breeze through. Trust me, it's one of the most important and frequently tested topics you'll find in your chemistry exams. Getting a good grip on what we cover today is going to set you up for some definite success. Look at this. This topic is a real gold mine for marks. In WAEC, it can be worth a massive 8 to 12 marks. That's across both theory and objectives. For you JAMBites, you're going to see 4 to 6 questions on it every single year, no fail. And for NECO, it's the foundation for understanding other big topics like redox reactions and qualitative analysis. So the message is clear. Mastering this topic isn't optional. It's absolutely essential if you want that top grade. So here's our game plan for today. We'll kick things off with the syllabus focus, then build a really strong foundation with electronic configuration and the unique properties of these metals. From there, we'll dive into the key compounds and reactions that you absolutely must know. Then, the fun part, we'll put our knowledge to the test by solving real past questions from WAEC, JAMB and NECO. Before we wrap it all up with a solid summary and some powerful exam tips. Alright, let's get right into the heart of it. We're starting with electronic configuration and properties. This right here? This is the foundation. This is what explains exactly what makes these metals so special. So first things first, what exactly is a transition metal? Now, the official definition, straight from your syllabus, is an element that has an incompletely filled d orbital, either as a neutral atom or in one of its common ions. I want you to remember that phrase, incompletely filled d orbital. It's the secret key. Everything special about them, their amazing colors, their ability to act as catalysts, everything, it all comes back to this single point. For the first row of transition metals, that's the one you need to know. The general electronic configuration follows this pattern you see on the screen. After the stable argon core, electrons fill the 4s orbital first, and then they start filling up the 3d orbitals. Now you might be asking, why does 4s fill before 3d? Well, it's simply because the 4s orbital actually has a slightly lower energy level. But as we all know, in chemistry, there are always exceptions, and your examiners love to ask about them. And here they are, the 2 big exceptions you must memorize for your exam. Let's look at chromium. You'd expect its configuration to be Ar3d4 4s2. But nope. To get to a more stable half-filled d orbital state, one electron actually jumps from the 4s orbital to the 3d, giving us Ar3d5 4s1. And it's a similar story for copper. Instead of the expected 3d9, it prefers a fully filled and much more stable 3d10 configuration. The reason for both? Simple. Extra stability that comes from having half-filled or fully filled d orbitals. Now, listen carefully. This is a rule that trips up so many students. When a transition metal forms an ion, which electrons are lost first? The answer is always the ones in the outermost shell. Think about it. Even though we fill the 4s orbital before the 3d, the 4s orbital, with its principal quantum number of 4, is further from the nucleus than the 3d orbital. Therefore, the 4s electrons are always lost first. Look at the example with iron. To form the Fe2+ ion, it loses its two 4s electrons, not the 3d electrons. Please commit this rule to memory. So all of that unique electronic structure leads us to these 5 characteristic properties you see here. Variable oxidation states, the formation of colored ions, their catalytic activity, complex ion formation, and paramagnetism. This table sums them up perfectly. And remember, every single one of these properties is a direct result of that incompletely filled d orbital we talked about. Now, let's break them down. Okay, let's look at the first 2 in a bit more detail. Variable oxidation state simply means they can lose different numbers of electrons to form different ions. A classic example is manganese, which can have an oxidation state from +2 all the way up to +7. This happens because the 3d and 4s electrons have very similar energy levels, so it's easy to remove more electrons from the 3d shell. Secondly, the formation of those beautiful colored ions. This is because of something called d-d transitions. In simple terms, when light shines on a solution, the d orbitals absorb some of that light's energy, which makes an electron jump to a higher energy d orbital. The color we see is the light that is not absorbed. That's why copper 2 sulfate solution is blue and iron 2 is pale green. Next up, they are fantastic catalysts. The ability to just switch between different oxidation states allows them to speed up reactions. You already know the famous examples: iron in the Haber process for making ammonia, or vanadium 5 oxide in the contact process for sulfuric acid. They provide a new, easier reaction pathway. They also form something called complex ions. This is when the central metal ion uses its empty d orbitals to accept pairs of electrons from other molecules or ions, which we call ligands. A perfect example is the tetraamine copper 2 ion, which has that beautiful deep blue color you see in the lab. Excellent work! Now that we've got a handle on the properties, let's focus on the specific compounds and reactions that WAEC, JAMB, and NECO absolutely love to ask about. This is where the theory gets real and practical. Let's start with iron. You must know the difference between ion 2 and ion 3. The Fe2 plus ion is a pale green color, and it can easily be oxidized to the Fe3 plus ion, which is a yellowish brown color. Now, the key test for Fe3 plus, especially in your qualitative analysis practicals, is when you add a specific reagent to get a deep, intense blue precipitate called Prussian blue. For your exam, the crucial thing is to memorize these colors: pale green for Fe2 plus, yellow-brown for Fe3 plus, and Prussian blue for the test. Next up, we have chromium with its very famous pH-dependent equilibrium. In an acidic solution, you get the orange dichromate ion. But if you add an alkali, the equilibrium shifts to the right and you form the yellow chromate ion. It's a perfect example of Le Chatelier's principle in action. And of course, if you add acid back, it shifts the equilibrium back to the left, turning the solution from yellow back to orange. The key takeaway for you is this reversible color change. Alright, let's talk about potassium permanganate, KMNO4. This compound is a very, very powerful oxidizing agent, especially when it's in an acidic solution. You must memorize this half equation. The permanganate ion, where manganese is in +7, gets reduced to be Mn2 plus ion. Now, the most important part for your practicals and titrations is the dramatic color change. It goes from an intense purple to completely colorless. That's what makes it so useful in titrations. It acts as its own indicator. The moment the solution stays faintly pink, you know the reaction is over. Fantastic! You've got the theory down solid. Now, let's see how these concepts actually show up in your exams. We are going to solve real past questions from WAEC, JAMB, and NECO together. Come on, you can do this. Here's our first one, coming straight from WAEC 2019. It's a titration question. It says 25.0 centimeter cubed of 0.1 m dm cubed Fe2 plus was titrated with 0.02 m dm cubed KMNO4 in acidic medium. Calculate the final oxidation state of manganese.
Now, this looks like a complex calculation with all these numbers, right? But wait, could it be a trick question? Yes, it is a classic trick question. All those numbers are just there to distract you. The question is simply testing if you remember the core reaction we just discussed. In an acidic medium, permanganate is always reduced to the manganese 2 ion, which is Mn2+. And what's the oxidation state of Mn in the Mn2+ ion? It's simply +2. That's the answer. C. Knowing the fundamental reaction just saved you from doing any calculation at all.
Okay, let's try a JAMB question from 2022. It says, the catalyst used in the contact process is, and it gives you 4 options. This is a perfect example of a direct recall question. JAMB loves to ask this to test your knowledge of industrial chemistry. And the answer, just like we covered in our properties section, is vanadium 5 oxide, V2O5. That is option B. These are easy, quick marks for you to grab as long as you memorize the key industrial examples straight from your syllabus. Finally, let's look at a NECO theory question from 2020. It's about as direct as it gets. State 3 characteristic properties of transition metals. These should be very easy marks if you've been following along. And the answer comes straight from that summary table we covered earlier. You just need to list any 3 from our list. They exhibit variable oxidation states, they form colored compounds, they have catalytic activity, or they form complex ions. If you remember that table, you've just bagged 3 easy marks. Simple. Fantastic work on those questions. I'm really impressed. Now, let's pull everything we've learned together into a final checklist that you can use for your revision. This is to guarantee your success on this topic. Please, I need you to do something for me. Take a screenshot of this slide right now. These points are the absolute non-negotiables you must memorize. Ion formation, 4 s electrons are lost first. The exceptions, chromium and copper. Color, it's caused by DD transitions. And finally, the key redox reactions for permanganate and dichromate. Note the oxidation states and the number of electrons transferred. And here are my final powerful tips. First, practice balancing redox equations until you can do it in your sleep. Second, memorize all the color changes. They are so important for your practicals. And finally, watch out for trick questions about zinc and scandium. Remember our definition, a transition metal needs an incompletely filled d orbital. Well, the Zn2+ ion has a completely full d orbital, and the Lc3+ ion has a completely empty one. So they don't behave like typical transition metals, and their compounds are usually colorless. Don't let them trick you. You have done an absolutely amazing job today. Seriously, by going through all of this, you have turned what might have been a confusing topic into a guaranteed source of marks for your exams. I am so confident in you. You've got this. If you found this lesson helpful, please do me a favor. Like this video, share it with your classmates and friends who are also preparing for WAEC, NECO, and JAMB. And subscribe to our YouTube channel right now so you don't miss the next topic. Also, make sure you visit ExamKP.com for thousands of free practice questions and answers. Let's go and smash these exams together.